thing about the magnetic unit is that it involves not only the math, but also like almost like a physical aspect to it, okay? And being able to visualize it and describe what you have. Now, what you have to be careful of in terms of your description. So, if you look on that assignment from yesterday, and so let's talk about question number 7. So on question number 7, here's what you've got. You've got this diagram that says, what is the current direction in the wire, figure 24/7? And here's what you want to look at. And the same thing is going to be true on number 8. So here's the visual that you have to have. You've got a circle, and then you've got the compasses pointing around them. And you have, this is going to be important, that the red end of the compass is pointing in a particular direction. So remember, a compass is defined by the direction that the north end points. So what this means is that, and you have to have this visual, this wire, the way it's drawn, is like the cross-sectional end of the wire. So this wire, like here's the plane of your paper. The wire is like this, okay? So imagine you're looking down. This is the leap of faith that you have to take. Imagine that you're looking down and you're seeing the end of the wire, okay? And then you have the magnetic field around it like this. Now, keep in mind, they're just showing you one region. In reality, there isn't just one magnetic field. It isn't just one line. This is just where we put the magnet. This whole thing is around this whole thing. We just look at one little sample size. So here's the deal. So in the simplest application, which is going to be more complex after today, in the simplest application of the right-hand rule, you wrap your fingers in the direction the magnetic field is going, and then your thumb indicates the direction of the current. So if you wrap your hands in this direction, so here's this wire, the magnetic field around it is going like this, which means your thumb is pointing upward. Okay? Now, this is where you have to be cautious about how you describe the motion or direction of the current or the magnetic field. If you just say, oh, the current is pointing up, I don't know what up means, and I'll show you why. I don't know if you say up, I don't know if you mean in the plane of the paper pointing towards the top of the page, or do you mean up like it's going out of the page? Okay? So up is too vague. I don't know what up means.
What if I say out of the page?
Now out of the page I can live with. Okay? But if you just say up, I don't know if you mean going towards the top of the page or out of the page. Okay? So like on number 7, you want to say out of the page. Okay? Because up is too vague. Big Mike.
On number 8, if I put like in the plane of the page, is that fine? Or do I not have to?
What if we say positive on the z-axis?
Say out of the page, dude.
Okay.
Okay.
What?
For the explanation, can I actually write the rule?
Yeah. Now, on number 8, again, it's the same situation. What current direction in the wire on figure 24A? So here's the wire. Now, here's what's different on number 7. On number 7, here's the plane of the paper. The wire was coming out like this. On number 8, the wire's in the plane of the paper. Okay? It's going like this. It's not up. It's flat like this. Now, you've got to use the right-hand rule. So what you've got over here is that you've got X's on this side, and you got dots over here. So, 2 ways you can do this. Right-hand rule. So, if you take your hand, your thumb, and you know X's are over here. Do X's go in or do X's go out?
In.
X's are like the pirates. Arr! Arr! Dig from these buried treasure. So, in this situation, your fingers would be pointing into the page. Which direction does your thumb point?
Down.
Down. So, in this situation, again, just don't say down, okay? Because I don't know what down means. But if you say down in the plane of the paper, that's something I can live with.
Yes, clearly the answer is down.
Obviously.
I'm just saying.
So down into the plane of into the
Because here's the point.
Would it actually be
Don't even talk, bro.
So,
How do we miss it?
here's why I don't like just the word down. Just like I didn't like the word up on the other side on the previous question. If you just say it's down, I don't know if you mean down like this or if you mean down like that. Okay? Because there is a big difference between the two of them. Okay? Big difference. On problems, for example, on problem number 2, it says you've got, using the data from table 24.1, determine what approximate distance from wire carrying current 10 amps the magnetic field would equal that of a refrigerator magnet. So yes, you've got to go look on that table and find the relative strength of that. So if you look on table 24.1, it gives you different magnetic field strengths. And that's on page
773.
huh?
773.
773. So notice that the field strength is measured in Tesla. Okay? Hence a shout out to Nicholas Tesla. So what's going to be important if you look at the surface of the Earth. So right now, we are all in a magnetic field. Okay? We're all in a magnetic field, 5 times 10 to the negative 5th. Kind of small, but yet important. It's enough that we can use it. So, when you're looking at this, it's got the refrigerator magnet 5 times 10 to the minus 3rd. Obviously, that varies, but this is kind of the ballpark 5 times 10 to the minus 3rd. So, your answer to number 2 should involve a 4. I'm just saying,
Because
I don't know.
I mean, it depends.
Well, it's in the
Yeah,
back.
can you
why
say-
not just put it in?
ChatGPT.
we're actually using the KMS.
Hey, yeah, we're in the
Okay.
we're in the KMS system, by the way, Michael.
So, let's talk about question 29. So you got an unmagnetized metal sphere, okay, brought toward the north pole of a magnet, the sphere is strongly attracted. So, here's what you want to look at. So on 29, the metal sphere itself has what we call magnetic domains. But the magnetic domains are kind of like all over the place. So where's that magnet that was here? Okay. So one of the things that I can do is like I can attach, so the paper clip itself and this binder clip right now are not attracted to each other. But if I put the magnet on the paper clip, so what that's done is that it's taken the magnetic domains that were in the paper clip that were completely random, and they said, hey, I'm going to make you a magnet. So now that becomes a magnet.
Oh.
Okay? So by putting it on a strong magnet, I've made the paper clip a magnet.
Yeah.
Because now I've taken the magnetic domains that are in the paper clip and made all those line up in one direction. So this now has become a magnet. But if I take that off, then the magnetic domains flip out and they go back to a non-aligned system, and it's no longer a magnet. Big Mike.
Is there like a way to make something a magnet without touching it to a
With the anvil like we talked about yesterday.
Yeah, but other than that, not really.
Or with electricity.
Do they have to actually
Well,
touch?
but that's,
Electromagnetic.
we'll get into that later. So, I touched, but, and it doesn't make any difference. If I put the binder clip on here first, that now becomes the magnet, boom, paper clip, now it becomes the magnet. Does that answer your question? So it doesn't make any difference if I use the north or the south pole, it's just how you align those magnetic lines. Okay, are we good? Hopefully that was a nice, short, easy assignment. Yes, ma'am.
So we're disagreeing on number 3. Can you explain the very first question?
Okay. On question 3 or problem 3?
Question 3.
Okay. So on question 3, here's the story. You're in the southern hemisphere. Does the compass still point north or south? So where's my globe? Hey, Big Mike. Yeah.
I need to play with you with that.
I need to
Now, here's the weird part about our Earth's magnetic field, and thank God we have one. So, here's our rock. Imagine inside of here is a big magnet. It really isn't. We have a molten iron nickel core. That's what's circulating. That's what's creating our magnetic field. So, if you take a magnet towards the North Pole, that means that the north end of that magnet is going to be attracted to the south end of the magnet that's inside the Earth. Okay, so this is where this gets a little bit wonky. Okay, what we call the North Pole, we call it the North Pole because a magnet that we've defined as being that side being north, which is completely arbitrary. Okay, we could have called it blue and white, left, right, doesn't make any difference. Cat, dog.
West.
Louise, whatever. We chose to call that particular direction north. So, what that means is that the north end of that magnet is pointing towards the south end of the magnet that's inside the Earth. Okay? So the North Pole is technically the South Pole of the magnet. Okay? Does that make sense? Now, the Confederate designation, so there's the north end of the pole. So which direction to the magnetic field lines point?
North to south.
North to south or south to north?
North to south.
North to south. It's the Confederate designation. So these field lines are coming out like this and coming in like this. Okay? So no matter where I am, and this is why this magnet, as I go around, okay, so here I am at the North Pole. So as that goes around like this, so even when I get to the equator, if I'm at the equator, that red end is pointing towards the North Pole, which is really the South Pole with the magnet inside of it. So even if I'm in the southern hemisphere, like this, that north end is still pointing north. Or otherwise, compasses would be fairly worthless because then you'd have to recalibrate everything when you cross the equator. Okay? So it's still going to follow as if I take this and I move this around like this, okay? That North Pole, even if I'm down below here, that North Pole of this magnet is still pointing towards the South Pole of that magnet up there.
Is that the difference between pure north and magnetic north?
Yes. So technically magnetic north changes. Our North Pole has been drifting a little bit, and it's actually been drifting more because it like wobbles. Okay? So they always have to go through and like readjust the North Pole location.
Wait,
So Santa Claus has to move his shop.
Oh, yeah.
so when the Earth thing flips and the south becomes north again, do the compasses flip?
Yes.
But we just have the experience
But
that history.
they think there might be a period of time where we have no magnetic field and the compasses will be worthless.
Oh, Bert, you're gonna die.
Yeah,
Wait, what if you're
Nobody
lost?
your point was,
once you cross
What if you're lost in the Amazon?
Does that
Huh?
Yeah, what if you're lost in the Amazon and then suddenly
I thought we needed the magnetic field for atmosphere.
Huh?
It has a magnetic
If it's an
I think
extended
so.
period
You
of
need
time,
a compass
bad
to
things
use
are
a
going to
map.
happen.
That's what I said.
Look at the sun.
You think I'm gonna let that
So
happen?
is that what
It isn't like we get to
the web.
vote.
The sun is
Okay.
Bert, why are you chill with this right now? This is some
There's nothing I can do about it. That's like me being upset about the times, okay?
Bert,
I don't
well,
like
let's
the
not-
times.
Bert, you started a
No,
solar
why is this
farm.
a
I'm
big
gonna
deal?
go protest the times.
You started a solar farm.
Yeah, I'm gonna.
Alright, over under
What you
5.5
call
years.
this
Hey,
I'm taking over on that.
Yeah, why
I'll
does
take
it
the
matter?
under on
Because
that.
you're always two steps behind.
Okay, anything else? What you gonna try salt? Get back
I
into
don't think
them.
you've ever
So
been
stop
staking
your
precedent.
Why would I try